Here we're going to look at a pretty interesting family of integrals. So they're indexed by natural numbers n, and we have I sub n, so that'll be the nth one of these integrals, is given by the integral from 0 to n times pi over 4 of 1 over 3 times sine to the fourth x plus 3 times cosine to the fourth x minus 1 dx. And in order to find a closed form for this, we're going to do a couple of things. So the first thing is we're going to notice that we can write in plus 1 as in plus jn, where jn is this following integral. So it's the integral from n pi over 4 to n plus 1 pi over 4 of 1 over this same denominator dx. And then after we prove this, this is going to be pretty short, we'll prove that I1 is equal to pi over 4, and then we'll prove that Jn is also equal to pi over 4 for all n bigger than or equal to 1. And that'll give us all of the tools to inductively come up with the value of In. Okay, good. So let's get to it looking at this thing right here. So notice that Jn is equal to In plus 1 minus In. So that's all we really need to do to calculate Jn. So let's do that. So notice we have Jn, and if you're keeping track, that's actually the forward difference operator of this sequence defined by these In's. So we could write it like that if we wanted to. This is like a discrete version of the derivative. So we have delta In. So that's going to be equal to In plus 1 minus In. And so that's going to be equal to the integral from 0 to n plus 1 times pi over 4 of, and instead of writing that whole function down because we're not doing any integration here, I'm just going to draw a box. So we have that box, and so that represents this whole thing. And now from that, we're going to subtract the integral from 0 to n times pi over 4. Again, this same box dx. Great. But now we're going to use a pretty common fact from Calculus 1 that says the integral from a to b is the same thing as the integral from a to c plus the integral from c to b. So maybe let's just recall that over here. If you have a is less than c is less than b, the integral of something from a to b is the same thing as the integral from a to c plus the integral from c to b. Okay, great. But then if we move this integral from a to c over here, we can see that we can apply that to this system that we have in this case. So that is going to be the integral from, so we have n pi over 4 up to n plus 1 pi over 4. And now for completeness, maybe I'll just put this function in here. So we have 1 over 3 times sine to the fourth x plus 3 times cosine to the fourth x minus 1 dx. But that's exactly how we defined Jn over here. So good, we have established this first fact. Now that we've established a formula for our recursion, let's look at these two following things that we need to still do. So we need to calculate I sub 1, in other words, the first element from this sequence, and then we need to find this common difference between any two subsequent elements, Jn. We're going to show that both of those are equal to pi over 4. So let's go ahead and look at this I sub 1 first. So we have I sub 1, that's going to be equal to the integral from 0 to just pi over 4 of 1 over 3 times sine to the fourth x plus 3 times cosine to the fourth x minus 1 dx. So now what I'm going to do is multiply the numerator and the denominator of this thing by secant to the fourth power to clear this cosine to the fourth power down to just a 1. And that's going to help us simplify. So let's go ahead and do that. So I'm multiplying the numerator and the denominator by secant to the fourth x. So let's see what that gives us. So we still have the integral from 0 to pi over 4. And now we have a secant to the fourth x in the numerator. And then we have 3 times sine to the fourth over cosine to the fourth, because here we're obviously going to use the fact that secant to the fourth is the same thing as 1 over cosine to the fourth. So that's going to give us 3 tangent to the fourth x, and then plus 3, so that's what we get from that, and then minus secant to the fourth x, and now this is all dx. Okay, fantastic. Now the next thing that we want to do is make some sort of substitution, and the substitution that we will make is we will let t equal tangent of x. So let's see what that gives us. So if t equals tangent of x, then dt equals secant squared of x dx. So the derivative of tangent is secant squared. And then furthermore, when x equals 0, that tells us that t equals 0 because we know tangent of 0 is 0. And then when x equals pi over 4, that means t equals 1 because the tangent of pi over 4 is 1 because sine and cosine are the same at a 45-degree angle. Okay, fantastic. So let's see what we get out of this. So now we have the integral from 0 to 1 because we've gone from our x bounds of integration to our t bounds of integration. So now I'm going to look at this numerator and notice that I can decompose it into a secant squared x times a secant squared x. And I'm going to take one copy of that secant squared x and combine it with the dx. So I've got my little earmuffs there. But now this is equal to dt as we saw over here in our substitution. Okay, great. And then the next thing that I want to do is, since we're trying to put this all in terms of t, which was our substituting variable, I'm going to take the secant squared and then further rewrite that as 1 plus tangent squared x. Great. And then I'm going to do the same thing down here. So I'm going to take this secant to the fourth and write it as 1 plus tangent squared x all squared. And now that gives me a clear path to make my substitution. So notice in the numerator I have 1 plus t squared. That's what I get from 1 plus tangent squared. And now in the denominator I have 3t to the fourth plus 3, and then minus 1 plus t squared squared. So that's what I get from this term right here. And then finally I have dt, and notice that my dt term gobbled up one of those secant squareds. So now let's multiply out this 1 plus t squared squared term and see what happens. So that's going to give me t to the fourth plus 2t squared plus 1. Let's see what that leaves us in the denominator. So we've got the integral from 0 to 1. We have 3t to the fourth minus t to the fourth because we have this minus sign right here. So that's going to give us, in the denominator, 2t to the fourth. Good. And then now I have minus 2t squared. And then finally I have 3 minus 1, so that's going to be plus 2. And then I still have this 1 plus t squared in the numerator, so let's just go ahead and write that. 1 plus t squared in the numerator, and then this whole thing is dt. Okay, good. So now let's go ahead and move this up to the top and then we'll continue on. So we've worked down the first term in our sequence to the following integral. So I have factored a 2 out of the denominator, giving me a 1/2 outside of the integral. Then I have the integral from 0 to 1 of 1 plus t squared over t to the fourth minus t squared plus 1. And now I'm going to use this nice trick where I multiply the numerator and the denominator by 1 over t squared. So let's go ahead and see what that gives us. So notice we're going to have to group those and then distribute. So that's going to give me half, and then I have the integral from 0 to 1. So I'll have 1 over t squared plus 1, so that's in the numerator. And then in the denominator, I have t squared minus 1 plus 1 over t squared dt. The next thing that we're going to do is cleverly rewrite the denominator by completing the square. So let's look at how that's going to work. So we've got t squared minus, and now I'm going to take that number 1 and write it as t over t, and then I have plus 1 over t squared. So I've almost got a perfect binomial squared. I've got a term squared here, a term squared here, and then their product here. So notice if I had a 2 here, then I would have a perfect square binomial. So that's what I'll do. I'll put a 2 in there, but that means what I've really done is I've subtracted an extra 1 from the denominator, so I can get around that by adding 1 to the denominator as well. So in other words, what I've done here is I've subtracted 1 and added 1. It's just one of the ones the one I subtracted ended up here, and the one I added ended up here. So I haven't changed anything at all. Okay, fantastic. But now notice we can group the first 3 terms and then factor them. So that's going to be t minus 1 over t quantity squared plus 1. The motivation here is twofold. For one thing, it simplifies this denominator, and for another thing, notice if you take the derivative of this inside thing here, you get the numerator. So we're setting up a u substitution. Okay, so now let's go ahead and rewrite the integral using this trick. So we have 1/2 the integral from 0 to 1 of 1 over t squared plus 1 over t minus 1 over t squared plus 1 dt. Now I want to make another substitution in order to simplify this, and since we went through all of this work of completing the square in the denominator, we're going to substitute for this thing that is squared in the denominator. So in other words, I'm going to take this and set it equal to u. So let's go ahead and let u equal to t minus 1 over t, and notice that's going to make du equal to 1 plus 1 over t squared. We can think about that 1 over t as t to the minus 1, so we take the derivative and a new minus sign comes out. Now we need to change our bounds of integration as well. So notice when t tends towards 0 from above, which is really what's happening with this lower bound of integration because this thing is discontinuous there. That's the same thing as letting u tend towards negative infinity. And also it's important to notice that here we're coming from above because we can't really take the total limit as t approaches 0 because that doesn't exist. There are only one-sided limits here. Okay, and then the next thing that we'll do is say what happens when t equals 1? Well, if t equals 1, then u equals 0. Sorry, this should have been a u up here. Okay, great. So notice that all of this right here is u, and all of this up here is du when I combine it with my dt. So that's going to give me half, and now I have the integral from minus infinity to 0 of 1 over u squared plus 1 du. But this has a nice antiderivative. It's the inverse tangent, so that gives us 1/2, and now we've got the arctan of u, and then we're evaluating that from minus infinity to 0. Just keeping in mind that evaluating it at minus infinity is really taking a limit. Okay, so plugging in 0, the inverse tangent of 0 is 0, and then the limit as u approaches minus infinity of the inverse tangent is minus pi over 2, so that's something good to keep in mind. So that's going to give us, in total, 1/2 times pi over 2. Notice this is a lower bound of integration, so the sign gets switched. So 1/2 of pi over 2 is pi over 4. So that establishes this fact over here that we've been working at. Now we've got one less fact to check, and that is that these j-ends are all pi over 4. And we're going to do these in a case-by-case process. We need to look at the even ones, and then we'll also look at the odd ones. So our first case will be if n is even, and that's going to make n equal to 2m, where m is some natural number. So let's see what that gives us. That means we have j sub 2m is going to be equal to the integral from, so that's going to give us m times pi over 2. And then up here, that's going to give us m times pi over 2 plus pi over 4. So m pi over 2 plus pi over 4. So notice our length of our interval is still pi over 4, which is kind of obviously what we need it to be. And then we have 1 over 3 times sine to the 4th plus 3 times cosine to the 4th minus 1 dx. Okay. Now what we want to do is notice that we've got some periodicity within this integral, and we can exploit that by making a substitution. And the substitution that we will make is x equals y minus m times pi over 2. But that's going to give us the fact that dx is exactly equal to dy because we're just scaling it by a constant. And then we can notice that that's going to change our bounds of integration. So I'll just do it right here. So this lower bound of integration is going to go to 0 when we change from x bounds to y bounds. And then our upper bound of integration is going to change to pi over 4 when we go from x bounds to y bounds. Now that we've changed the bounds of integration, let's go ahead and see what happens to the integrand. So here we've got the integral from 0 to pi over 4 of 1 over 3 times sine to the fourth y minus m pi over 2 plus 3 times cosine to the fourth of y minus m times pi over 2, and then minus 1, and then dx. Okay, so now technically there are a lot of cases to consider, but they all boil down to just being able to delete this minus m times pi over 2. So let's talk through that a little bit. So if m is 1, for instance, then we get sine to the fourth y minus pi over 2, but that's going to be cosine to the fourth. Notice any negative sign that would have been built into there by the phase shift is going to be eliminated by taking an even power. And then cosine to the fourth is going to switch to sine to the fourth in that case. But now if m is 2, for instance, we have y minus pi, and sine turns to minus sine in that case. But again, because we're taking an even power, that disappears. And then similarly, if n equals 3 or 4, so really technically you need to look at all values of m mod 4, but they all turn into just being able to delete this little phase shift. So that's really good. Now we can go ahead and rewrite that as the integral from 0 to pi over 4, and now we have 1 over 3 times sine to the fourth of y plus 3 times cosine to the fourth of y minus 1 dx, but notice that is our original integrals I1, which was equal to pi over 4. So good. We have proven this for even values of n, so now let's go ahead and clean up the board and prove it for odd values of n. Okay, now we're ready to look at odd values of n. In other words, that means we can write n as 2m plus 1. So in this case, that's going to make my jn equal to the integral from m times pi over 2 plus pi over 4. So that's not too hard to see just by plugging in 2m plus 1 everywhere you see n right here. And then that's going to go all the way up to m times pi over 4 plus pi over 2. So notice that's still an interval of length pi over 4, which is exactly what we need it to be. And then we have 1 over the same thing, so we have 3 sine to the fourth x plus 3 cosine to the fourth x minus 1 dx. Now we're going to do exactly the same substitution as we did before, so we'll let x equal to y minus m times pi over 2. That's going to make dx equal dy. And that's going to have the effect of changing these bounds of integration from pi over 4 up to pi over 2. And then I can just go ahead and replace my dx down to dy because they're the same. And then notice if I plug this value of x into this integrand, I will, similarly to what we just did, get sine to the fourth y plus cosine to the fourth y, both multiplied by 3. Again, that's because this integrand has period pi over 2 like we described in the last case. Okay, good. Now this almost looks like what we just had, except now instead of the integral from 0 to pi over 4, we have the integral from pi over 4 to pi over 2. So now I'm going to skip the details because you run through the exact same integrals as you did before when we were calculating I1. It's just the bounds of integration are a little bit different. So I'll just say similarly. So it turns out if you run through those exact same substitutions that we did before, so again we'll turn this into an integral involving secants and tangents, then we'll make a substitution where t equals tangent, and then finally we'll complete a square and then make another u substitution. You'll end up with the exact same integral. You'll have 1 over u squared plus 1 du, but the bounds of integration will be different. In this case, the bounds of integration will be 0 to positive infinity, and I forgot a half out here. But again, this one is pretty straightforward to do. So we can take the antiderivative. We'll get 1/2 the inverse tangent of u. We need to evaluate that from 0 and then take the limit as u goes to infinity, which I'll just write like that. The limit as u goes to infinity of the inverse tangent of u is pi over 2, so we get 1/2 of pi over 2, which is pi over 4. But this is what we get for the odd value. We already determined that for n equals even, we get pi over 4, so we have established this last fact. Okay, so we've established these 3 facts that we were going to use as tools, and now we're ready to prove our final claim, and that is that in equals n times pi over 4. And so let's maybe look at a little proof of this. So notice our base case, if we were to do this by induction, would be that I1 equals 1 times pi over 4, but we already calculated by hand that I1 equals pi over 4. Now we're going to go ahead and suppose this is true for n equals k, and then we'll look at ik plus 1. But notice that ik plus 1 is equal to ik plus jk, but we already proved that jk was equal to pi over 4 for everything. So we have ik plus pi over 4. But then that's going to be equal to k times pi over 4 plus pi over 4, but that's going to be equal to k plus 1 times pi over 4. But that finishes this induction proof that I sub n equals n pi over 4. So in other words, the value of this integral is n times pi over 4. So we kind of overdid it with induction at the end because this is like fairly obvious maybe. But I think it's never wrong to kind of over-explain the details. Okay, so I think that's a good place to stop.